All right, let's start. Good morning. So today I want to discuss some examples and exercises regarding this HK integration. Talk a little bit about certain properties of these gauges, or rather what you can enforce using gauges and this notion of delta fineness. And then once we're done with these, we're going to transition to differential calculus. Like I've been saying so far, differential calculus, or rather its formal account, is rather more, it's a lot closer to what you've encountered so far in Calc 1. Ultimately, if we're trying to differentiate a function f, well, we're just going to look at something like this. This is this ratio, and then we're going to take h to 0, and this is going to define for us f prime at this point x. Of course, we're going to learn how to do things with this. But you see, the one thing that we're going to need to cover before transitioning to differential calculus proper is, well, we need to make sense of this limit. So far, even though we did take limits of functions, these functions that we were taking the limits of were defined in the limit point. But as you see, in general, this expression is not quite well defined for h equals 0. So we need to kind of make sense of this expression. So if you're looking at Taylor's book, this is chapter 4.1, as I believe, the first section of differential calculus. So we're going to have to discuss that a little bit, and then we're going to go forward with our differential calculus. Okay. So first I want to give a class of examples that is going to be useful in the problem set to this Friday. Namely, using gauges, how do you force specific points to be sampled? Okay, so this is the main thing. So you should think of gauges as a device that allows you to control the length of the intervals of the partition that you're looking into in a very fine manner. A lot finer than just coming up with a bound on the mesh. Because if you're bounding the mesh by some number, by some small number, you're sort of saying, well, any pixel is allowed to be at most this long. But if you're allowed to use a gauge, then what you can do is, well, based on where the problematic points are, you can sort of fine-tune your gauge so that near problematic points, near singularities of your function, the intervals are even more controlled. Okay? And so remember, I told you there are two types of gauges, essentially. One is, so any gauge is, by definition, a positive function defined on this. One is if the inf of that gauge is, if it's a positive number. So that sort of is pretty much the same thing as using meshes. But you're also allowed to use gauges whose imps are 0. Okay? And so for instance, say I want to make sure, I want to come up with a gauge delta such that for any sampled partition that is delta fine relative to it, say the point 0 has to be sampled. And so this I can achieve like so. Consider this. Okay. This is the diagonal, as usual. Say I want to force, I want to have something like this. Delta should be so that for any sample partition that is delta fine, 0 has to be sampled. Well, imagine this. Imagine I take here this height, and then something like this. Imagine this is my delta. It's my gauge. As you see, the inf of this is 0. Okay? So this is one of those more special kinds of, or nicer, or this is one of those gauges that allow more control, you should say. So let's try to understand what sort of a geometry delta fineness implies in this case. And how did we do this? Well, we look at triangles, right, whose corner is on the graph of delta. And so for instance, if I were to look at this point, it's maybe something like this. I'm just looking at the right angle thing. And so this is pi over 4, sorry, 45 degrees. And likewise this. So this length, delta of 1, is the same thing as this. So if you want, this is exactly 1 minus delta of 1. Okay? And then I take this triangle and I keep sliding it sideways in such a way that always I make sure that its apex is on the graph. Meaning, ultimately, if I take this triangle and keep sliding it this way, for instance, if I were to look at this point right here, okay, you see now the height is a lot smaller. Okay. And since the graph of delta is always underneath y equals x, unless I sample this point, 0, I will never be able to cover 0 using my sampled partitions. Which means, relative to this delta, for any PS sampled partition, if PS is delta fine, then 0 is a sampled point. That is to say, 0 is in the image of S. If you want, you can think of this contrapositively, or you can try to prove this using contradiction. Say, for this specific delta, there is some sampled partition PS such that relative to that sampling function, 0 is not sampled. Okay? Which means I'm not sampling this point, but I'm sampling some other point somewhere here. But then delta fineness requires that each pixel in my partition is of bounded length. But you see, this delta is so much smaller compared to y equals x, which means that if I were to sample any other point here, the associated pixel will not be able to cover 0. Okay? So this delta decays way too fast for that to happen. And that's why this is the case. Okay. This takes a while to get accustomed to, but this is the main thing that makes the difference between Riemann and HK integrals. Yeah.
Would that be the case for any gauge that's underneath that y equals x line?
Yeah, exactly. Yeah, so you can do something like this. If you look at the Fonda textbook, I think the example there he gives is something like this. So this is y equals x, and he looks at x over 2. That would work as well. Of course, why would I choose this or this? Well, this kind of decays faster, which means that this would allow me to control whatever sort of a singularity I would have much better than this. Okay. Very good. And you see, you can do the same trick at a midpoint, at finitely many points, whatever. So for instance, you can do something like this too. I'll erase this. Here's another example. Let's look at this. Okay. Say I'm trying to sample 1/2. I want to come up with a gauge such that for any sampled partition that is delta fine, 1/2 is for sure sampled. Well, what I can do is this. Okay, so I'm trying to sample this point, 1/2. Again, look at the two lines with slope 1 and -1. That gives you sort of like an envelope. Okay. And then you can make your delta something like this. This is the graph of delta. Again, by the same reasoning, relative to this gauge, any sample partition is going to be forced to have 1/2 as a sample point. And you can do this with finitely many points, ultimately. You will take finitely many points. Let's do one more, perhaps, like this. Again, I'm looking at the lines with slope 1 and -1. Okay, say I'm trying to force sampling these points. Then I can come up with something like this. The specific formula doesn't quite matter at this stage because there's no function specifically given to me that I'm trying to integrate. I can look at this. This would force sampling at least these 2 points, for instance. It looks scary, but with HK integrals and this delta fineness and stuff, you can just like draw the pictures, at least in one dimension, and sort of experiment quite a bit. Okay, so here's an exercise. 0, 1 is my closed and bounded interval. I'm going to look at a family of functions. Alpha is a positive number, and for each alpha, I have one function, f sub alpha, that takes positive values. Okay, x sent to x to the minus alpha. So for instance, think of like alpha could be 1, so that's 1 over x. Alpha could be 1/2 and stuff, or alpha could be 3 over 2 or whatever. Then f sub alpha is HK integrable if and only if alpha is less than 1. And in this case, in fact, the HK integral is 1 over 1 minus alpha. Okay. I'll let you sort of try to compute this. Maybe we'll discuss it later, or maybe it will show up in a problem set later or something. But essentially here, you're using that idea, okay? So no matter what alpha is, okay, there's always an asymptote as x goes to 0. There's a blow up. And right from the get-go, for instance, since these guys are not bounded, I can immediately say that these guys are not Riemann integrable. Although probably you did learn how to integrate this. You did something like this in Calc 1. Right, so you said, I'll just write down the function as well. X to the minus alpha dx. Okay, so this is, you see, not quite something that we defined so far. Because like I said, this is unbounded and this is undefined, but there are things called improper integrals. And so you say, in order to integrate this, how I'm going to do, so the way I'm going to integrate it using Riemannian theory is, I'm going to take epsilon to 0, and I'm going to, in fact, integrate from epsilon to 1. Okay, so that's, for us, an improper Riemann integral. Improper. Riemann integral. And assuming that you have the fundamental theorem of calculus, right? So you would say, what is this? Limit as epsilon goes to 0, and I should probably say epsilon is positive also. Right, so x to the 1 minus alpha divided by 1 minus alpha, assuming alpha is not 1. Say alpha is not 1. And then you evaluate x from epsilon to 1. And then when you take the limit of this, this goes to 1 over 1 minus epsilon. That's how you would have calculated this in Calc 1. And so whenever you can calculate something using the tools that you learned so far, you should have this expectation that with this fancier thing too, the answer should be the same. What is the difference? Well, first of all, we haven't covered what this means, this improper integrals. For us, Riemann integrability, first and foremost, was immediately implying that the function is bounded. So this is not quite something that we covered so far. Although, eventually, we will sort of mention this improper integrals slightly more formally also. But you see, this improper Riemann integral in the world of HK integrals is a proper definite integral. And how do you actually compute something like this? Well, you fixing epsilon, you come up with a gauge that has one of these businesses, okay? And so this is at 1. Okay, at 1, any f sub alpha is at 1, and then the function sort of blows up. And really, alpha tells you how fast that blow up happens. Okay. There's an asymptote. For your gauge, what you're going to do is you're going to have something like this. Okay, that will be, let's say, delta sub alpha. That also depends on epsilon. But the point is, you're going to engineer your gauge so that the way it decays as you're reaching the singularity compensates for the way your function blows up. Because ultimately, this too is a Riemann sum. You're going to multiply the length of the base times and the length of the side. And so the sides are sort of growing like this. In order for the sum to stabilize at a finite point, so finite number, what you need to do is you need to compensate. So somewhere here, for instance, the height is going to be something like this. Well, in order for things to converge, this has to decay fast enough so that its space is very tiny. Okay, that's the main idea. The calculation of it gets somewhat sort of messy, but this is all there is to it. Okay, it's a very nice exercise to actually compute this. Okay, what I want to do is I want to give this example. Now, remember, this is the essential example of a bounded function, right, that fails to be Riemann integrable. Earlier, we talked about how this is not Riemann integrable because its upper Riemann integral is 1, and the lower Riemann integral of it is 0. But you see, this is HK integrable, and its HK integral is 0. Claim. And the HK integral of f is 0. Now, how to do this? Maybe I should ask you, what are the sort of bad points in this function, for this function? There are good points and bad points. The point of using a gauge is to control the bad points. Give you a couple seconds. This is really an important sort of example. It's very discontinuous, of course. It keeps jumping between 1 and 0. So the bad points are either rationals or the irrationals, okay? Because this guy keeps jumping between rationals and irrationals. If I were to ask you to approximate this function, at least pointwise, using step functions, could you come up with a sequence of step functions that at least approximates it, this function, pointwise? We know it cannot be approximating uniformly, because if it were, it would be Bourbaki integrable, which implies Riemann integrable, but we know that this is not Riemann integrable. So you cannot approximate this using step functions uniformly. But you can still do it pointwise. And so, any guesses?
So making a sequence of step functions going between 0 and 1 just constantly make it pointwise conversion?
In a sense, but well, I mean, in a sense, you have to use spikes.
Okay.
So here is a sequence of step functions that approximates this guy pointwise. Meaning, the bad points are the rationals here. Okay? The bad points are the spikes, which are the rationals. So, the graph of f jumps between 0 and 1. I'm going to use step functions made up of, so basically you start with sigma 0, let's say. It's a constantly 0 function, and then you start introducing spikes. So for instance, I'm not going to keep writing all of these, but imagine it like this. Start with this, and then put one spike here. So now, that's a step function. It is 1 at 0 and 0 otherwise. Add another spike. Okay. That's a second step function. Now add another spike at 1/2. Okay. Add another spike at 1/3, then 2/3. Okay. 1/4, 2/4, I already have something. Then 3/4 somewhere here, and so on. Okay. Yeah.
Is the thought with this like essentially you like list out all of the all of the rational numbers?
Yes.
And their sequence is just sampling from.
Exactly. Exactly. Very good. So I'll leave it to you to write this explicitly. What I'm really doing is exactly what your colleague is suggesting. Think of it like this. I can take the collection of all rational points, rational numbers between 0 and 1, and essentially come up with a sequence that runs through every single one of them. Like so. It's harder to write down the formula for it, but imagine this. Start at 0, go into I, okay? And it's going to be like so, in this order. So, 0, 1. 0, 1/2, 1. 0, 1/3, 3/3, 1. 2/3, sorry. And then 1. And then 0, 1/4, 2/4, 3/4, 4/4. And then 0, 1/5, and so on. Okay, that's my sequence. I'm running through every single rational point this way, which if you want to be more formal, you can show using induction. You would induct on the denominator, for instance. You see, it's harder to write down the explicit formula, even though if you're good with combinatorics, you can do that, and like this is useful to be able to do. Never mind, that's a sequence. It's well defined. I'm overcounting certain things. Well, what you can do is you can get rid of some of them. In fact, I'll do it like this. So you start with this sequence, and then the rational points you keep repeating, you discard. That's a subsequence. Discard this. Okay, discard all instances of 1. Okay, discard all instances of 1/2, discard this, and so on. You keep going like this. This is how Q bullet is defined. Consequently, we have a sequence in the interval 0, 1 that is a bijection onto all the rational points. Thus, the image of Q is I intersection rationals, and for any two distinct indices, the corresponding rational numbers are distinct. N not equal to M implies Qn not equal to Qm. Okay, I'll leave it to you to write down a specific or explicit formula for Q. Write an explicit formula for Q bullets. Okay. Which ultimately also gives you a sequence. You can sort of engineer this a little bit, modify it just a little bit, and you would be able to obtain a sequence of step functions that converges pointwise to f, which is very nice. Hang on a minute. That's true, yes, okay. Converges pointwise. Okay. So using this, I'll define for myself a gauge. Now, that points are the rational points for this. So based on our heuristic, my gauge should be small for integers, for rational points. I'll do it here. So what do I need to do? I need to say, given any epsilon, there's a gauge such that for any sampled partition, PS, the associated Riemann sum is bounded by epsilon. Right? That's what it means for f to be hk integrable, and simultaneously, it's hk integral being 0. Okay, and define delta by this. X sent to, let's say, epsilon over 2 to the n, if x is q sub n, if x is one of these rational points, 0, not 0, let's say 1. 1 otherwise. Okay? You see, this is a positive function. It's a valid gauge to look into. But its inf is 0. As n goes to infinity, inf of this is 0. And when you see this, how do you sort of try to make sense of this? Oh, irrational points are fine. You see, I'm not even controlling that much. Rational points are the bad points. I'm sort of keeping the gauge very small there. Now, if I were to take then, if PS is delta fine, you'll show in the problem set due this Friday that there's always a sample partition given any gauge. So there is one like this. Well, you look at the associated Riemann sum. Okay. It looks like this. Now, first of all, the sample points, so in the sum, all I need to look into are the pixels whose sample points are rational, because otherwise f is 0. So I can say sum over all pixels whose sample point is rational, in which case this is just 1, okay? S like this times, or this, so this is 1. I'm just adding the lengths of all pixels whose sample points are rational. But then, since I'm assuming that PS is delta fine, for P, whose sample point is in rationals, its length is bounded by twice this. That's what it means for PS to be delta fine. Okay? Because any point in this pixel has to be within delta of S of P of the sampled point, which means this is bounded by twice an expression of this form. Okay? So you're adding essentially finitely many terms of this form for finitely many integers, but that's sort of like a geometric series, whatever. And so this is bounded by epsilon times C for some C that is independent of everything else. For some universal is what people would say. Universal C. In other words, Riemann sums are, if you want you can do this too, doesn't matter. Ultimately, Riemann sums are arbitrarily close to 0, and that's what it means for this guy to be HK integrable. And I'll leave it to you to compute this universal constant. Probably it's going to be like 3 over 2 or 1 over 2 or something like this. Okay. Very bizarre. Does this kind of make sense? When we tried to do the same thing with Riemann integration, our control was not fine enough. You could say, oh, let the mesh be, small, but then insofar as the mesh bound is a positive number, well, you're not able to guarantee the length of the intervals in the associated partition to be sufficiently small, which consequently made it so that the Darboux aperture does not go to 0. In fact, it goes to 1 in this case. But you see, if you're allowed to use gauges, in other words, if you're trying to compute the HK integral, then you can really fine-tune the mesh control in a sense. You can localize the mesh control to different points. Okay. I think that's all I wanted to say, at least for now, regarding integral calculus. We'll come back to it once we're done with the basics of differential calculus, because ultimately we're doing all this stuff so that we can do a fundamental theorem of calculus. And essentially the main reason why HK is a lot nicer, despite the fact that you can also integrate a bunch of things, is that automatically, if you have a differentiable function, its derivative ends up being HK integrable. That is not quite correct for Riemann integrability, for instance. There are functions whose derivatives are not necessarily integrable with respect to Riemann, with respect to Lebesgue, whatever. So ultimately, you should say, oh, we're sort of investing in technology here for HK integrals, whatever, which ultimately is going to help us simplify FTC, fundamental theorem of calculus. Okay. Any comments or questions? Yes, go ahead.
Does the definition of gauge, which means delta parenthesis x, always a piecewise?
Not necessarily. It could be a constant function too. It could be any function, insofar as it's always a positive function. It could be crazy like this, okay? It could be a nice continuous function. It could be just a constant, okay? But typically, fine control, so gauges that allow you to control finely are, bad looking like this. Let me put it this way, yeah. Why? Because we're doing integrals over closed and bounded intervals. So for instance, if you were to try to use a gauge that is continuous, is also positive, by the maximum principle, it has a minimum, and its minimum has to be a positive number also. So if you're just using continuous gauges, that's the same thing as using constant gauges, ultimately, which is going to give you the Riemann theory. It's not going to give you anything new.
So the uniqueness is that type of definition.
Yes, exactly. This is where these kind of crazy definitions is where this theory shines. Exactly. Yeah, I mean, I'll give you this exercise if you want. We could have started with HK integrals and then defined Riemann integration within HK integrals, like so, for instance. We could have said, it's the characterization if you want. Let f be a function taking real values, then the following are equivalent. F is Riemann integrable for any epsilon. There's a constant gauge such that for any sample partition constant gauge such that for any sample partition, if the sample partition is delta fine, PS delta fine implies, I should say, there is some R star, such that the associated Riemann sum is within epsilon of R star. Or I could have taken delta to be continuous. That's equivalent also. There's an R star. For any epsilon, there is a delta, which is both a gauge and continuous, such that for any PS, if PS is delta fine, implies that the associated Riemann sum is within an epsilon of R star. These are all equivalent. So using constant gauges is the same thing as Riemann integrability, and using continuous gauges too is the same thing as Riemann integrability. Yeah. In terms of nets, this net that is associated to HK integrals is a subnet of the net that is associated to Riemann integrals. So while the Riemann integral may not converge, the subsequence is possibly converging, or subnet is possibly converging. Pretty nice. Okay, any other comments or questions? I didn't include this subnet stuff because as opposed to subsequences, subnets are somewhat confusing. So we're kind of not discussing those, even in problem sets. But there is something called a subnet. Okay, differential calculus. So I want to go back to the metric space setting for a second and define limits of functions where the inputs, where at the limit the function is not necessarily defined. And so for this, I define something like this. I take a metric space X and a subset A. Its closure, which I denote by close of A, typically you would also see A with a bar of A is the set of all points X in X or X infinity in X, such that for some sequence, A bullet in A bullet converges to X star. Okay? So you should think of the closure of a set to be the set of all those points that are well approximable using points in A. You call A closed if it's equal to its closure, and you call A open if its complement is closed. And the nice exercise for this is closed intervals are closed in this sense, and open intervals are open in this sense. We're not going to use these too much beyond this definition for a limit, but for those of you who are going to take the 3220, the sequel class, you're going to spend some time discussing these in the case of Rn, whatever. Let f be a function defined on this subset, say taking values in some other set, for y, another metric space. I'll take a point in the closure, so X star be in the closure of A and Y star be in Y. Then I'm going to say that the limit of f of x as x goes to x star along A is y star if, well, it's a, we need to write that down. Then the limit of f as x goes to x star along A is y star if, we can use epsilon-delta here, for any epsilon, there is a delta such that for any A in A, if A is delta close to x star, then f of A is epsilon close to y star. Okay. In this case, we write limits, whatever, but we write perhaps, we put something that signifies that we're taking limits along A. So maybe we can use something like this. Okay, so if I didn't have this, you see x in A, that would be the standard limit that we've been using so far. I'm saying take the limit along A. Okay. I hope you can guess how this could be useful in the context of partial derivatives and stuff like that, for instance. Okay. In the case of x being the real line and A being an interval, we have this. I'll leave it as an exercise. If x is R And in fact, I don't need A to be an interval here. It can be any arbitrary subset. So A is some arbitrary subset. In fact, let's do it like this. I'll take A to be some interval of this form, open interval from lambda to rho. Say mu is some point in A, somewhere in between, and say I have a function f defined on A except at mu. Maybe there's an asymptote or something. Okay, maybe it's not defined there. A take away mu. So f possibly is not defined at mu. Maybe there's an asymptote. Okay. Then let's write it like this. This limit exists if and only if the so-called left and right limits exist and is the same. X goes to mu, and x, I'm going to say, is to the left of mu. And this time to the right of mu. So a limit of a function like this exists if and only if the sort of one-sided limits exist and they are the same. Yeah, I'll just say exist. Not super sophisticated compared to continuity and limits that we've discussed before. Okay. I have like a couple minutes. I think at this point I can just define differentiability. Much like with continuity, differentiability is a local property. That is to say, you first define what it means for a function to be differentiable at a point, and then you say f is differentiable if it is differentiable at every point. See, we switched differential calculus, and now our standing assumption is going to be I is an open interval. Okay. Differential calculus works a lot better with open intervals. I'm going to say that f is differentiable at x star if limit as x goes to x star of this exists. As a real number. Formally, people would describe or sort of denote the set along which they would take limits. But in practice, you would typically not write this. But if you want to be more formal, you would sort of add here x not equal to 0. So you're taking the limit along everything except x star here, technically, because at x star, this expression is not quite defined, which means that function is not defined there. Okay, so at the very least, we were able to define differentiability. Tomorrow, we're going to continue from there. Thank you. All right, let's start. Good morning. We're going to continue working on differential calculus. Today I'm going to take attendance, and We're gonna discuss some terminology. I need to set up some notation, definitions, and so on, so that we can have our nice sets of our classes of functions coming from differential calculus. And once we're done with differential calculus, we're going to connect it to integral calculus by way of the fundamental theorem of calculus, of course. And then we're going to be on our way. Okay. So standing assumption for differential calculus, okay, I'm looking at open intervals now. For continuity, integral calculus, I was naturally looking into closed intervals and functions defined on them. For differential calculus, it really works a lot better if you're using open intervals. Okay. Of course, if we're going to try to use integral calculus together with differential calculus, what you're going to see that I will typically again take an open interval, and then I'm going to restrict my function that is differentiable on this open interval to a closed and bounded subinterval. For instance, if I want to do something like a mean value theorem or something like that. Okay. Part of it is because when you're looking into closed and bounded intervals, even though you can still do differential calculus, you know, now you need to worry about defining the derivative of the function at these endpoints. And of course, if you're doing differential calculus and stuff like that, these are important matters. But for general purposes, I think it just makes things more technical. So I'm just going to focus mostly on open intervals. So here's first an exercise. I take two intervals I and j, and some function from I to j. In principle, j could be reals, but it doesn't need to be. Okay. And I take one point x star. I want to think about the differentiability of f at this x star. The exercise is that there's at most one lambda number such that if you were to take this limit, and so in the numerator you have f of x star plus h minus f of x star minus lambda times h, and then you take the absolute value of these, and you divide it by h, you're taking h to 0. And remember, I told you yesterday, technically this is not quite defined at h equals 0. So if you want to be more formal, under the limit you would put something like this. But most people would not write it like this. It's clear that this function is not defined there, and so on. There's at most one number lambda such that this limit is 0. Okay. Possibly there is none, but no matter what the function is, there's at most one. Okay. And if you know linear algebra, the next two parts are for those of you who know linear algebra. I could have stated this by saying there's at most one linear transformation from reals to itself such that the same ratio goes to 0. Or I could have said there's at most one affine transformation from reals to itself such that this ratio goes to 0. These are formally pretty much the same for one dimensions, but for those of you who are going to take the multivariable version of this, these are going to be the versions that you're going to use. Okay. The catch here is that any linear transformation from reals to itself is nothing but multiplying by a number. And any affine transformation of the reals to itself is something of this form. So in higher dimensions, of course, this is not quite the case, but we're not going to look into that. Okay, and so I defined this yesterday, but I wanted to do it again because there are multiple ways of writing the same thing, and depending on the context, so you might prefer a different formalism. Again, I take a function and an x star, a target point, and I'm going to say f is differentiable at x star if any one of these equivalent conditions hold. And as usual, I'm going to leave it to you to verify that these are equivalent. There isn't much math behind sort of proving the equivalence of these. It's just a matter of like rewriting things or changing the variable, whatever. So no matter what f is, there's at most one lambda. If there's at least one lambda, That means that f is differentiable. Or what I can do is I can basically rearrange this and essentially send lambda times h divided by h, which is just h, to the other side, and just realize this number lambda is nothing but the limit of this ratio. That's equivalent. Third way to write it is this: f of x star plus h equals f of x star plus lambda times h plus little o of h as h goes to 0. Now this was a similar notation that we saw for continuity. So I'm saying f of x star plus h is this plus higher order terms. So how do you read this? You say this is little o of h. Okay, that's how you read it. We're going to keep defining certain things, and toward the end of this class, I think I'm going to discuss this notation in more generality so that we have an understanding as to how continuity fits with this notation also. Okay. So I personally like this 1, 2, 3. I like to imagine f of x star plus h. In other words, if I have x star, and if I'm looking at differentiability at x star, obviously I'm going to take a nearby point. But instead of just thinking of this nearby point as something that is not quite related to x star algebraically, I find it a lot more convenient to think of x as x star plus h for some h small. So the way I'm imagining this is that, this x is a h perturbation of x star. Okay. So x is a small perturbation of x star. And here, h itself is the perturbation. This is the perturbation. Okay, we're going to discuss all these later. Yeah, so that's why I like 1, 2, 3. But if you want, you can also, instead of using x star plus h, you can just switch to x. And so, for instance, instead of having x star plus h here, you would have x. X stars stays the same. And instead of h, you're going to have the difference of x and x star. And the denominator 2, instead of h, you write x minus x star. And so 1 turns into 1 prime this way. 2 turns into 2 prime. 3 turns into 3 prime. OK. In this case, based on the exercise, such a lambda is unique. And therefore, you denote it by f prime of x star, or df by dx of x star. OK, it's a number. And you call it the derivative. And lambda is called the derivative of f at x star. Might look scary, but what it is that if you're taking this class, I guarantee you're familiar with what I'm doing here. It's not anything new. I'm just setting up the formalism so that we can develop the theorems and so on rather fast. Just like with continuity, if my function is differentiable everywhere, I call it differentiable. So f is differentiable if it is differentiable at x star for any x star. Nice exercise is that you can connect this to gauges. This exercise, again, is a matter of opening up the definition of this limit, for instance, in terms of epsilon and deltas. If it's differentiable, if and only if the following holds. differentiable if and only if for any epsilon there is a gauge on the interval I, positive function, such that for any x star and x star plus h in I, if h in absolute value is bounded by delta of x star, then, well, I want to say that ratio is bounded by epsilon instead of bounding that ratio, because then I need to say h should not be 0, whatever. I'm just going to send h to the other side and have this bound. Oh, yeah, write it like this. So I guess I should say there's a lambda. Lambda h in absolute value is upper bounded by h times epsilon. It's a gauge. Somehow this exercise is at the foundation of this idea that essentially hk integrals are defined so that the fundamental theorem of calculus works. We're going to see that in 2 weeks, or in 1 week, I guess, when we come back. Okay, what else? Let's see. While there is some notation for the class of differentiable functions, in applications, just differentiability is not often good enough. Typically, what people would require that f prime 2 is continuous, right? So because if f is differentiable, then for each x star, I have some number, which means that I can think of f prime as a function in and of itself. And so typically, people would require something from f prime also. The first type of a property, of course, is that you would require that f prime is continuous. That's called a continuously differentiable function. F is continuously differentiable if f prime exists and it itself is a continuous function on I. The class of all continuously differentiable functions, finally we get to raise this 0 to a 1. C1 is the class of all continuously differentiable functions. I should put here a J. Continuously differentiable functions on I, or from I to J, and inductively, you define CK functions to J for any k non-negative CK plus 1 IJ is the collection of all CK functions whose derivative is also continuous. Hang on. How do I want to say that? K times differentiable. How do I write this? Oh, f is differentiable. I see. It's better to set up the induction that way. F is differentiable, and its derivative is CK. Such that f is differentiable, and f prime itself is CK. So C0 is the continuous functions. C1 is the collection of continuously differentiable functions. C2 is the collection of twice continuously differentiable functions, meaning f is in C2, if and only if you can differentiate it twice, and the second derivative is continuous, and so on. Let's see, what else do I want? Let's define a diffeo. So in week 1, we talked about, or you saw in the problem set, the notion of a bijection. This was a function that was invertible in the sense of set theory. And then we transitioned to continuity. And there we saw that the notion of a homeomorphism is invertibility in the sense of continuity. Invertibility in the sense of differential calculus is a diffeomorphism. Okay? F is a diffeomorphism if f inverse exists as a function and both f and f inverse are differentiable. Likewise, you define a C1 diffeomorphism, C2 diffeomorphism, CK diffeomorphism if both f and f inverse are CK. Is a diffeo f such that both f and f inverse are CK. I'll add one more thing. You can take the intersection of all these k's to get C infinity. This is the collection of infinitely differentiable functions. I'll write it here. 0 to infinity, ck, ij. Okay. An important theorem. Let me see if I'm missing something. No, I'm not missing anything, so that's good. Here's our first theorem. It's not very sophisticated of a statement, but it's rather convenient. It's going to help us realize how these collections of differentiable functions relate to each other. Namely, as you increase the index, you're shrinking the subset. In other words, any differentiable function is continuous, and therefore C1 is a subset of C0, and CK plus 1 is a subset of CK, and so on. Let f be a function and x star be a point in I if f is differentiable at x star, then it is also continuous at x star. Consequently, I'll write it as a perhaps corollary. I don't think we used this so far. Corollary means it's another claim that is sort of a side byproduct of something larger. the more you increase the index, the smaller the subset gets. Okay. Let's do the proof. What do I need to control to show f is continuous at x star? Well, I need to control the distance between f of x star plus h and f of x star. Well, I'll take an h that is non-zero. And I'm trying to control this expression. I want to say that as h goes to 0, this goes to 0. That's what it means for f to be continuous at x star. Okay. Well, I see from the second characterization, in the numerator, I'm essentially seeing what I'm trying to control. So I'm going to divide and multiply by h. Like so. Okay. Now, as h goes to 0, since I'm assuming that f is differentiable at x star, the first factor over there, the ratio, is going to converge to some finite number, which is lambda, f prime of x star. And on the other hand, h in absolute value is going to converge to 0. But we know at this point, in such a situation, this whole thing goes to 0, as h goes to 0. As h goes to 0, this guy converges to f prime of x star. I guess I should say absolute value times 0. Not that it matters that much because this whole thing is 0. And that's what it means for f to be continuous. Okay. If this holds for any points, well, if you had a generally differentiable function, differentiable everywhere, at each point, it would be continuous. And consequently, if you had, for instance, a C1 function, it would be differentiable and its derivative would be continuous everywhere. But differentiability already implies continuity. So C1 would be a subset of C0, and so on. Okay? Now, I should mention, probably in the next problem set, which is going to be, after the break, there's going to be a problem about these inclusions being proper. That is to say, there are ck plus 1 functions that are not ck plus 2, and so on. Certainly, there are continuous functions that are not continuously differentiable, and so on. And there are functions that are C-infinity also. For instance, the exponential function. Exponentials, once you differentiate, give you back the same thing, which means that you can keep differentiating an exponential function. Or a polynomial function. If you have a function that, after finite derivatives, gives you 0, which is another definition of polynomial, actually, that's C-infinity. Now, once we're done with differential calculus and the fundamental theorem of calculus and the Taylor approximation and all that stuff, in the third part of the course, we're going to study real analytic functions. And so somehow the real analytic functions is an even proper subset of C-infinity. So we're going to look at, for instance, C-infinity functions, but then that means that we have infinitely many derivatives. And then we're going to ask, oh, if I were to take these infinitely many derivatives, put them in a series, does that series converge? In general, no. And so you can have C-infinity without that convergence. But for those functions for which the series of derivatives converge, that is real analytic. We're going to see that, and the notation for that is going to be c to the omega. Okay. Put it here. C to the omega ij. This is to be added later. For now, we're not going to deal with this because that requires that we study series and so on. Okay. Any comments or questions so far? So everything, despite all the notation, whatever, everything works pretty much how we are used to. I should mention in Calc 1 and whatever, people would typically use only C infinity functions, or C infinity except at finitely many points type of a function. Obviously, in this class, we're going to be rather worried about how many times you get to differentiate a function. Okay, so first derivative test, okay, I can use C1 for instance. For a second derivative test, that means that my function needs to be C2, whatever, because I need two derivatives to be able to say f double prime is positive, whatever. Any comments or questions? Yeah.
Can you repeat what are you trying to prove there?
I was trying to prove the theorem. This one. I assume that f is differentiable at x star. And assuming it, I wanted to show that it is continuous.
Okay, so you do direct proof.
Yes.
Start with assumption
Yes.
that f is differential.
Yes.
And now, and then at the final,
Yeah, I assume that f is differentiable.
okay,
And then I said, in order to show that f is continuous at x star, I need to show that as h goes to 0, the limit of this expression is 0.
to show it's continuous.
Yes. For any epsilon, okay, let's use the epsilons and deltas. This is perfectly valid as far as I'm concerned, okay? So epsilons and deltas, you see, the way I think about it is that obviously they are useful, but for fine matters, you should open up the epsilons and deltas. For if you can get away with it, you should not go down all the way to epsilons and deltas. That's my perspective on things. I'll use a different color. But still, it's good. Every once in a while, it's good to open up these definitions using epsilons and deltas to see, and it's sort of like a nice reminder for us also. Because once we discuss this little o, I'm going to fast forward even this. So this little o notation is going to help you sort of package this sort of an argument a lot faster also. So let's go back first using epsilon delta. So suppose f is differentiable at x star. We claim that f is continuous at x star. That is to say, for any epsilon, there's a delta, blah, blah, blah. That is, for any epsilon, there is a delta such that for any x in I, if x minus x star is bounded by delta, then f of x minus f of x star is bounded by epsilon. Okay, this is the definition of continuity, the epsilon delta definition, if you want. You see, what I was saying was that instead of using this x minus x star, it's better to think of this as h for differential calculus. Because for the type of differential calculus we're using, it's really important that nearby points can be algebraically represented. Okay? So differentiability in the context of metric spaces, it works really differently than the type of differential calculus we're doing. So I'm saying here, if you want, this is a change of variables. X is x star plus h. If you want to connect it to this, which means that h is x minus x star. That's my change of variables, if you want. Okay. Let epsilon be positive. Positive number. Ultimately, what did I do? Well, I tried to control this guy, this. I'll do it this way. Okay. Since limit as x goes to x star of f of x minus f of x star divided by x minus x star is this number f prime of x star, I can make it so that their difference is bounded by epsilon for some delta. There is a delta such that for any x in I, if the distance between x and x star is bounded by delta, that is to say, if my perturbation is at most delta, then the difference between these two of course, I should say probably x not equal to x star. Is bounded by epsilon. Rearranging, I can write this like so. So minus like this. This whole thing is upper bounded by epsilon times x minus x star in absolute value, which itself is bounded by delta, which means this is bounded by epsilon times delta. Okay. And so question? No? Okay. So what do I need to control? I need to control this guy, or this guy rather. Oop. Start with that. Subtract and add this term, and then use triangular. So I need to subtract this. And then distribute the absolute value to get this. Okay. Now this guy is bounded by epsilon times delta. And this guy is bounded by f prime of x star times delta, which means this whole thing is bounded by delta times epsilon plus f prime of x star in absolute value. Okay, so for any epsilon, there's a delta, such that for any x, that is delta close to x star, the thing I'm trying to bound is bounded by this.
So you do triangular inequality?
Yes, here. Right, so I subtracted and added this term, and then I split the absolute values. That would consequently only, that could only increase this quantity. And then the final trick you can do is for any epsilon, there's a delta, but then you can take this delta and replace it by this delta and, or rather the minimum of that delta and epsilon over 2. So what you can do if you want, you can take this delta to be upper bounded by epsilon over 2 if you want. Because you can always shrink your deltas. In which case, this whole thing would be bounded by something that decays like epsilon squared, which means that for sufficiently small epsilon would be less than epsilon. It's a really good exercise here too to realize that, in fact, underneath the hood, in this exercise, we talked about how differentiability corresponds to, for any epsilon there being a gauge. This is sort of like a differentiability gauge if you want. But likewise, for continuity too, you can write continuity in terms of for any epsilon there's a gauge such that something happens. So those two gauges are intimately connected. It would be really nice to come up with a relationship between the two. What I'm saying here is that any gauge that is a differentiability gauge also works as a continuity gauge, for instance, underneath the hood, if you keep track of the dependencies. Okay. Now, what I do want to do is, in fact, I want to fast forward this argument even further using this little o notation. This is sort of opening up, one way to open up this argument over here, write it more explicitly. Again, like I'm saying, it's like in the exams, for instance, I'm not typically expecting something like this. Sometimes you end up needing to do something like this, of course, because things are sort of too fine. You need to sort of control things rather finely. But this is a perfectly valid thing. It's kind of like a gauge, you see. You should be doing math like a gauge. It's like if something is problematic, it seems like, then you should sort of bring out the good, big guns and so on, and epsilons and deltas. But for most purposes, you should not be using the highly technical epsilons and deltas and whatever. That's sort of my perspective. Okay. But it's still good, of course, every once in a while to open up the more sort of tidy, higher level sort of arguments to see that everything actually works. Here's a third proof using little o. I'm just going to use little o first, then we're going to discuss what these actually mean. Well, I'll use a different color, blue, or red. Of the same thing. Okay. By differentiability, f of x star plus h is, well, f of x star plus f prime of x times h plus higher order terms. Right, so this plus f prime of this, I'll erase this part. times h plus little o of h in absolute value as h goes to 0. But this part is little o of 1 as h goes to 0, which means that this is f of x star plus little o of 1 as h goes to 0. And that's what it means for f to be continuous there. Okay. So this argument, using little o's, compress even this. Okay, kind of manages for you such limits. And now I want to talk about this little o notation and the big O notation. There's a similar thing. How many of you have seen something like this? Big O, little o. Typically, people in computer science see these kind of things. So these are what are called orders of magnitude. So somehow this gives you a way to talk about things approximately, but in a very precise manner. Okay? So if you have an algorithm, for instance, say matrix multiplication or whatever. So it's going to depend. So how long that algorithm is going to take to finalize is going to depend on the size of the input. But you want to say, well, how does that size scale with the so how does that time scale with the size of the input? Okay. And so that's why in a lot of sciences, statistical mechanics, whatever, where it becomes an important thing to be able to rigorously approximate things, this order of magnitudes ends up being really convenient. And the same thing holds for calculus also, of course. You can really fast forward a lot of things once you get used to this little o and big O notation. All this is to set you up for this Taylor approximation paradigm. So let me just say something first. If you see an expression like this, okay, I'm going to write down the formal definitions in a second. This really means, okay, f of x star plus h is f of x star plus something that converges to 0 faster than 1 does. In other words, this is something, right? So this is your error that decays faster than 1 does. 1 doesn't decay, so all you're saying is that this is some error that decays to 0. Error that decays to 0 as h goes to 0. People would often sort of not write this h or whatever. Often it is clear from the context. On the other hand, this, for instance, really tells you, well, I have this stuff, plus I have some error that decays faster than h does. Okay, h decays to 0 as h goes to 0. Okay, but whatever this is some error term that decays even faster. Okay, maybe h squared. Decays to 0 faster than h does. Again, as h goes to 0. And so I'm saying if f of x star plus h is this 0th order term, right? There's no h here. First order term plus higher order terms. In other words, f of x star plus h is f of x star plus f prime of x star times h plus something that decays faster than h does. Well, I can just say this whole thing is something that decays. So therefore, I can just take this and package it, absorb everything into one little o of 1. This is really convenient to be able to do, okay? Sometimes it gets confusing, but if you're careful, it's really convenient, even in sort of abstract math. Okay. So orders of magnitude. Orders of magnitude. Let's write it like this. Let X be a metric space, X star be in X. I'll take one function taking real values in X, or on X, and I'll take one bound function beta. That's basically kind of a gauge on X. Then we write f of X is beta of X, or big O of beta of X. Big O of beta of X as X goes to 0, rather X goes to X star, if there is a constant C and there is a delta positive such that for any X in X, if the distance between X and X star is bounded by delta, then f of X in absolute value is bounded by C times beta of X. Which means as you're taking your input near this X star, beta starts dominating f up to some constant. Okay? This is the big O. This is not little o. So this is big O. You would say f is big O of beta. So for instance, any polynomial with top degree, say 10, is big O of x to the 10. So 0 to n, ck, x to the k, of course I need c sub n to be non-zero. This polynomial is big O of x to the n as x goes to infinity. So if you're trying to control asymptotics of a polynomial like this, as x goes to infinity, all you need to do actually is to control the top degree monomial. You can just get rid of the lower degree terms. Okay. This is one. We're going to look at little o as well, and we're going to keep going from there. Thank you. All right, let's start. Good morning. Attendance again today. So today we're going to keep working on differential calculus. I want to spend more time on these orders of magnitude business, big O notation and little o notation. Typically, this is stuff that mostly applied mathematicians or applied people who apply math use, but in my experience, it's also very useful. These two symbols, because it allows you to compress a lot of information, get rid of sort of, in a sense, red herrings in certain estimates and stuff like that. Standing assumption, as is customary in differential calculus, we're assuming I and j are open intervals. This little o and big O notations, these are sort of more general, but we're going to transition to the interval setting in a second. Even before going into these, I want to mention this example, okay? This is perhaps one of the first contexts in which you encountered this. In calculus, you would probably see something like the sine of theta is approximately theta for theta small. Where would you use this, for instance? Well, you would see it. Well, maybe I should ask you if you had seen this before. For small angles, you can pretend that sine of theta is theta. In physics, people would use this and stuff, right? The main example that I remember is the case for the pendulum. You have a pendulum, so harmonic oscillator, something like this. And you have a mass. Say, I mean, you can talk about friction too, but let's forget about friction for now. There's a downward g, okay? And this is your theta, how much it separates, because based on theta, you sort of split the mass, whatever. In any event, you set up an equation that is second order using F equals ma, whatever. And so here, they say, oh, this is somewhat complicated because inside the function you're trying to solve, or rather, the function you're trying to solve is within a sine. Sine is nonlinear. This ODE, there's an ODE underneath. It's hard to solve, whatever. And then they say, but what you can do is you can linearize this. And essentially, you can pretend this situation to be the same thing as this situation. And now, this is the equilibrium position. And now, instead of your theta, you look at this position. Okay? And they say, oh, these two equations are approximately the same. That's what this means. Sine of theta is theta, or approximately theta for theta small. Of course, then, so this is sort of the physics or differential equations part. But when you go down to Calc 1, probably what they would do is they would take the limits of sine of theta divided by theta. They would use L'Hopital there and say, oh, look, the limit goes to 0, whatever. Or I guess it's a constant, whatever. You can do all these things. But I remember when I first saw this, I said to myself, well, surely sine of theta is also 0 approximately. Because sine is a continuous function. As the angle goes to 0, sine has to go to 0. And instead of pretending that sine of theta is theta, why not just pretend it doesn't even exist there? Of course, the fact of the matter is that both of these are correct. It's just that this is a 0th order approximation. This is equivalent to saying that sine of theta is a continuous function of theta. And this is a first order approximation. So with Taylor approximation, we're going to start looking into higher order terms as well. Okay? And already by the definition of differentiability, I'm saying it's a function that you can approximate up to first order. That's what I'm really saying. OK. So if I have a metric space X, I have one function taking real values and another function taking positive values only, and I fix a point, x star, then I'm going to write this. Okay? F of x equals big O of beta of x as x goes to x star. And this is how you read it, big O. Okay? If this happens, if there's a constant c, such that if your x is close enough to the target point, then f is dominated by beta up to this constant c. Okay? So the point here is that you're really talking about the behavior of f. I'm going to give examples of this in a second, slightly more easier than these. And so you say, I don't want to worry about these constants, whatever. I worry about asymptotics. That's all I worry about. And so you get to absorb a bunch of constants, whatever, as you're trying to approximate things into this big O. This is big O. Little o says something stronger. So f of x is little o of beta as x goes to x0, or x star, if the ratio of them goes to 0. This means that maybe beta is decaying as x goes to x0, whatever, but for sure, whatever beta is doing, f does it even faster. Okay? That's the only way this ratio to go to 0. Okay. So for instance, instead of looking at these, let's first look at these. Here are some examples. The function x, okay, is big O of 1, for instance, as x goes to 0. We're of course suppressing a bunch of things, but imagine that I'm imagining my functions on R. Why is that? Because think of how this looks like as x goes to 0. This is my function. This is my f. It doesn't look like x, but imagine that is x. And then 1 is like this. Okay, so this is the function 1. This is the function x. Okay? Now, I'm not saying when x is far away from 0, 1 bounds x. That's not what I'm saying. What I'm saying is if x is close enough to 0, then this is going to be an upper bound for this. Okay? You see, x I can bound in absolute value by, well, just 1 for delta. In this case, if you want 1/2. Meaning, if x is less than 1/2, okay, I don't really care about the specific value of delta at this point here too, because you see this big O and little o is all about approximations. So you're trying to develop a language that manages a bunch of epsilons and deltas underneath the hood without being very specific, which you get to use to approximate things or think about things rather fast. Does this make sense? X is big O of 1. Let's do more examples. X is not, oh, I'll write it like this. X is also little o of 1 as x goes to 0. Why? Because x divided by this is just x. As I take x to 0, this limit goes to 0. Okay? So how do I read this? I say, oh, x is a function that decays faster than 1 does. In this case, 1 doesn't decay. All I'm saying is that x is a function that decays to 0. But for instance, x is not little o of x in absolute value. Why? Again, if I were to look at the ratios of these two, okay, I take x to 0, the ratio exists, the limit exists, but it's not 0. Because the way this decays matches exactly with the way this decays. Okay? X squared. X squared is, again, big O of 1, whatever, but it's also big O of x in absolute value as x goes to 0. Why is that? Because if x is small enough, certainly x squared is going to be dominated by x. Imagine 1/2. 1 over 4 is its square. It's much smaller. Yeah? You see, once you get comfortable with this notation, it really helps you sort of fast forward a bunch of thinking. I'll draw it here. Like this. So this is your x function. That's what I'm using as my beta. Okay? And what is x squared? It's like this. It's a parabola. You see, if x is far away from 0, certainly x squared dominates x. But that's not what I'm worried about. I'm worried about big O as x goes to 0. If x is less than 1, you see, the parabola is going to be underneath x. I'm going to be able to dominate x squared. Okay? Does this make sense? Okay. So there's a bunch of examples like this you can come up with. You can look at big O or little o as x goes to 0 or x goes to infinity, whatever. Typically, for differential calculus purposes, we're going to take x to 0. And in fact, we're going to take h to 0. You're going to probably see a bunch of problems about this big O and little o and whatever. And so just it reiterates, for instance, what I can say again is that sine of x is big O of 1 as x goes to infinity. Why? Because it's a bounded function. Sine of x times x, you see this is not big O of 1 because it's not a bounded function. But it is big O of x as x goes to infinity. Okay? You see, that says that for purposes of asymptotics, as x goes to infinity, you can pretend that x times sine of x is x. This sine of x is not going to do much for calculation purposes. Okay? You can pretty much pretend that it is not even there. Now, of course, this comes with a bunch of fine print. But the way you get used to it is by using these more and more and transitioning between statements like this and back to sort of epsilons, deltas, whatever. And then eventually it sort of clicks. Okay? Okay. I think that's all I wanted to say about these. Okay, good. Now I want to do chain rule. I guess I'm not going to use this. I'll write it here. I wrote it there, but I'm going to need one more interval here, so I'm just going to take another one. I, J, K, B. Non-empty open intervals. So f be a function from I to j, and g be a function from j to k, so that I have this composition well defined. X be a point in I, and say f is differentiable at I, and g is differentiable at f of x star. If f is differentiable at x star, if f is differentiable at x star, and g is differentiable at f of x star, then the formula you know holds. Then g composed with f is differentiable at x star, and we have the rule, the formula. I'll just do it like so. What is it? The derivative of the composition at x star is g prime composed with f at x star times, or maybe I should say like this, g prime at f of x star times f prime of x star. That's a better notation. Because at this point, we don't know if g prime exists as a function. I'm just saying it exists at f of x star. Now you see, you can use the standard epsilon-delta definition for differentiability to prove this. But what I'm going to do is, in fact, instead I'm going to just use the big O notation, or rather the little O notation. So essentially, if you have an expression like this for differential calculus, using this little o notation or little o definition of differentiability, you can basically approximate everything up to first order and sort of expand everything. And once you do that, pretty much a lot of these calculations end up being an algebraic sort of verification. So I start like this. Just to reiterate, f is differentiable at x star, for instance. If and only if I have this expression. F of x star plus h is f of x star, 0th order term, plus some number times h plus higher order terms as h goes to 0. So up to higher order terms, I'm saying this is nothing but this. And vice versa too. Goes backwards as well. And so if I can take this quantity, it's a number, it's a well-defined number, and if I can show that it fits into this for g composed with f, I would be done. Maybe I should write it explicitly so that it's clear. It suffices to show that g composed with f of x star plus h is 0th order term plus the first order term, but I had this candidate given to me by the statement. So I'm going to take this number. It suffices to show this. You remember yesterday how we talked about the fact that if there's a number like this, there's a unique one, and differentiability is the existence of such a number. OK. So I'm going to start with this, and I'm going to start opening it up. You see, with little o, you're going to see it's so much more pleasant than trying to use epsilons and deltas. I'll do it here. OK, this, of course, is the same thing as g applied to this guy. I know that f is differentiable at x star, which means that I can expand this.
You already know f is differentiable already.
Yes.
So that you can write that thing.
Yes. Here I'm using the fact that f is differentiable at x star.
Nothing to do with g. Yeah?
No. Yes. Here I use the fact that f is differentiable there. OK. Now call, you see, now I want to use the fact that g is differentiable at f of x star. In order to do that, well, let's call this thing k. call this k. Okay. So what does that mean? I'm defining k to be some function, in fact, such that its difference between this and this decays faster than h does as h goes to 0. You see, the logic of using literal law is sort of kind of backwards in a sense. So this is the same thing as this. Now, using the fact that g is differentiable, I can expand it again. This at k plus little o of k in absolute value as k goes to 0. Resubstitute. So this, I guess I can at this point write it as g composed with f. I have this. Instead of k, I have this expression. I'll just do this slowly. And I have this guy. Expand everything. Usually you don't write all of these steps. I'm just doing it for once so that we're sort of displaying. Okay, expand this by this, plus this times little o of h as h goes to 0, plus little o of k as k goes to 0. So I just took these little o stuff, and I'm just expanding everything algebraically. So we're almost done. And as you see, just by doing this, I was able to get the 0th order term and then the 1st order term. And you see, this number just popped up merely from this algebraic expansion. So if I can show that this junk, okay, this error, is little o of h, I would be done. Right? Because that's what I'm trying to get. That's the format I'm trying to get. Well, first of all, when I see this expression, okay, I read it as this. Oh, this is some number. I don't really care what this number is. Some number times some function that decays faster than h does as h goes to 0. Okay? Well, the same thing has to hold for this number times this as well. So you can absorb this number into this. This is little o of h as h goes to 0. How about this? How do I think of this? I'm saying to myself, this is some function that decays faster than k does as k goes to 0. But any function that decays faster than this as k goes to 0 also has to decay faster than h does, which means this is also little o of h as h goes to 0. And if you add two things that decay faster than h does, you're going to again end up with something that decays faster than h does. So that means that this whole thing is little o of h as h goes to 0, which is the end of the proof. Now, some people really dislike such thoughts because this is like kind of like pseudoscience a little bit, it seems like. But it's not. If you really think about it thoroughly, everything makes perfect sense. And in case you have concerns, always you can turn this into an epsilon-delta proof. But of course, I'm going to leave that to you to do. So you rewrite this using epsilon-deltas. So try to control the difference between this and this by something that depends on h. Prove using epsilon-delta. In the textbook, in the Taylor textbook, that's what they do. And essentially, the argument is the same, in fact. It's just that these little o stuff manages epsilons and deltas for you underneath the hood. And so the perhaps only contentious issue is that little o of k is the same thing as little o of h. Or rather, any function that is a little o of k is also little o of h. And why is that? Because, well, k is a function of h. And so I'm saying k is something of the form h up to some constant times something that decays faster than h does. So that means that if I have some function that decays faster than this, well, it has to decay faster than h also. That takes a while to get accustomed to, these little o stuff. I'll grant you that, but like I said, I think this is a very good opportunity for you to get accustomed to this, because this is, a lot of people use this little o notation and big O notation and stuff like that. And depending on the context, even though people might be using more advanced calculus, probably you're not going to see epsilon and deltas that much. But you're going to see little o's and big O's quite a bit. Okay? So that's that. Here's a corollary to this, chain rule. If I have a diffeomorphism, that's a scary sounding word. What does it mean? It just means it's a function that is differentiable, has an inverse. Its inverse is also differentiable. Write it here, corollary. If f from I to j is a diffeo, then, first of all, for any x in I, f prime of x cannot be 0. And for any y in j, the derivative of the inverse at y is 1 over f prime at f inverse of y. Why is that? We just applied the chain rule to f composed with f inverse. You know that it is just identity. That's what it means for f to be invertible. So, so if I were to take an x, for any x, I have that f inverse composed with f of x is x. Differentiating, this gives you 1. This gives you, by the chain rule, something. Right, so the derivative of the outer one evaluated at the inner point times the derivative of the inner one, this has to be equal to 1. And that proves everything, because I'm saying for any x, I have one number and another number. These are well defined, such that their product is 1. That means that f prime cannot be 0. because otherwise the product cannot be some number other than 0. And furthermore, because neither of these are 0, I can just take one to the other side to get the other equation as well. So that's pretty cool. Yeah. And geometrically, I hope this makes quite a bit of sense as well, because we know, geometrically speaking, inverting a function corresponds to reflecting its graph along y equals x. So if I have something like this, say this is my f, it seems like it is x squared. F of x equals x squared. Its functional inverse, of course, is x to the 1 over 2. Something like this. Okay, so this is f inverse x to the 1 over 2. Right? I'm not talking about the reciprocal. I'm not saying it is 1 over x squared. It's the functional inverse. But ultimately, if I were to look at the derivative of f at whatever point, derivative geometrically is the same thing as the slope of the tangent line, right? If this is x, here is f of x. Okay, I should be looking at the derivative here. Well, it doesn't look like it, but these are sort of symmetric. Turns into this. So I wasn't able to draw this picture properly, but if you were to use a plotting graphing calculator, that would draw you properly. So the slope of this is going to be sort of the reflection of this, geometrically speaking. And algebraically, this is the formula. So the slope to the tangent line, to the line tangent to the graph of f inverse, is going to be sort of the reflection, or rather it's going to be the slope of the reflection of the line tangent to the graph of f at the corresponding point. Pretty cool. Comments or questions about this? Now, in the textbook, at this point, I'm going to mention one thing, but I should say, in the textbook, there's something about, there's a condition, there's a theorem about when a function is a diffeomorphism. So that is what is called inverse function theorem. Ultimately, what you want to do is, you want to look at the converse of this corollary. You want to say, if I know that f prime is non-zero, can I conclude that f is a diffeomorphism? Okay? Yes, in a sense, and we're going to discuss that. But as opposed to the textbook, I'm going to do it after we cover mean value theorem, because mean value theorem is more foundational. I want to say a couple things. First, I'll give an example of a diffeomorphism, or something that perhaps is not a diffeomorphism, just so that we can compare homeomorphisms and diffeomorphisms. Okay? So consider this. This is a very important example for what is to come. I'm going to take I to be -1 to 1, open, and think of f from I to I that takes x to x cubed. Okay, it looks like this. This is the graph of f. Okay? Now, if you want, you can include the endpoints too. It doesn't really matter that much. I should ask you, is this a homeomorphism from the interval to itself? This was in the context of continuity. Yes. OK. How can we argue about this? It's clear from the picture, but what you can say is, well, x cubed is a product of many continuous functions, because we know x is continuous, which means that x times x is also continuous. So f is continuous. Furthermore, it's defined on an interval, and its image is an interval also, and it is strictly increasing. By this theorem that we discussed a while ago, you can conclude that it's a homeomorphism. So this is an invertible. This is a nice function from the perspective of continuity. But this guy is not a diffeomorphism. OK? Why is that? Because at x equals 0, the derivative is 0. We just showed that for diffeomorphisms, derivative cannot vanish. OK? That's a very subtle point. And then, trying to connect this back to Calc 1, for instance, you may want to start thinking about first derivative test, whatever, right? If you have a function, you want to differentiate it, set that equal to 0. Those points should tell you stuff about the function. But you see, here at x equals 0, f prime is 0. Therefore, we're going to define all this too, but I hope you remember some of this at least. X equals 0 is a critical point of f. But x equals 0 is neither a local minimum nor a local maximum. OK? So that first derivative test works the other way around, actually. OK. Just to write these down, or just to summarize, I'll write a couple words here without this example. F is a homeo. It is strictly increasing. Continuous. Image is interval. Then by theorem, gives that it's a homeomorphism. Gives f is a homeo. This was a theorem that we discussed toward the end of continuity. However, it's not a diffeomorphism. Because f prime at 0 is 0. And by the corollary, that cannot happen for a diffeomorphism. OK? It is a differentiable function. OK? It's a differentiable function. It has an inverse. But the inverse is only continuous. It's not differentiable. Why? Because geometrically, what is f inverse? Well, you look at y equals x. Flip the picture. In fact, there's a vertical asymptote at x equals 0 for f inverse. It becomes vertical, its graph. It's very bizarre. OK? So f is differentiable. It's a homeomorphism. Its inverse is continuous. But it fails to be differentiable, the inverse. Another thing, too, for instance, from Calc 1, we're used to saying things like, f prime being positive is the same thing as strictly increasing. F prime being positive, in a sense, well, let me put it this way. Both f and f inverse, in this case, as you see, is strictly increasing. These are homeomorphisms. They are strictly increasing. But it is not necessarily true that f prime is always positive. That also fails. It goes backwards, in fact. OK? This is a foundational example. See? In the world of differential calculus, things are more restrictive. It also means that you can do a lot more, of course, in a sense. I personally like differential calculus and integral calculus type of stuff more compared to continuity. Remember, I was telling you how continuity is like very flexible, whatever. I should also mention, in Calc 1, in sort of integration, probably you did U substitution. Almost all U subs you used is a diffeomorphism. So diffeomorphism is essentially another word for a U substitution. You cannot quite use a homeomorphism for a U substitution because there is no sort of connection between how much distortion there is. Because you probably remember, once you do U substitution, there should be a correction factor coming from U prime. Okay? If you don't have U prime, then who knows how much your integration is, or your integral is being changed. Okay? So diffeo is the same thing, approximately the same thing as a U substitution. Okay. Any comments or questions about any of this? Yes?
You say that x at 0 is a critical point?
Yes.
In what sense?
I haven't defined it specifically, but literally we're going to define a critical point to be a point where either the function is not differentiable, or if it is differentiable, the derivative there is 0. Yes, we're going to get there. I was using the notion of a critical point in the sense of Calc 1. We're going to take our time and define it rigorously. Yes. But you see, differential calculus is so much closer to what you learned in Calc 1. It's just that things are a little bit more, technical, and as usual, we worry about whether this holds compared to this holds, whatever. And typically in Calc 1, what you end up doing is, well, you typically focus on cases like this, or people don't quite emphasize, oh, this doesn't work the other way around. Or you might say, oh, this test, there's this test. If this, then that. If that, the other thing. If this third condition, then the test is inconclusive, whatever. You might see something like that. But in Calc 1, we don't quite worry too much about in which direction implications work. But of course, in this class, we do. OK. So I want to give one exercise. As usual, there are certain algebraic properties of differentiable functions. You should be able to add them, whatever. These are all the way you expect. I think I'm going to do only one of these and leave the remainder to you. So exercise. Let fg, two functions taking real values, be differentiable. Then their sum is differentiable. And the derivative of the sum is the sum of the derivatives. Any scalar multiple of f is differentiable. And of course, you can take the scalars out. The product of two differentiable functions is differentiable. And their derivative is the product of the derivatives. And if one of these is always positive, say, then you can also differentiate the ratio, and it gives you something. OK? Nice. Yes, this is wrong. OK? You never do this. OK? This is very good. I always do this when I teach this class. I'm glad you caught it. That's not wrong. That is not correct. But there's a correct formula. It's more complicated than this. Remember, With integration 2, the product of functions is integrable, but the integral of the product is not the product of the integrals. Okay? Integration is more complicated. That's why you have integration by parts. For pretty much the same reason, even though the product of functions is differentiable, the derivative of that is not going to be merely the product of the derivatives. Okay? Product rule, or Leibniz or whatever. That's very important. The correct formula is this. I'll write it here. Right, so derivative of the first one times the second plus first one times the derivative of the second one. So f prime times g plus f g prime. That's the correct formula. It's more complicated, but you know, such is life. And likewise, there's a formula for ratios. I'm not going to write it. Now, like I said, I'm going to leave these to you. I want to do this product rule. And again, I'm going to use the little o notation. My idea is this, okay? Whenever I see algebraic expressions like this, I say to myself, I should be able to get away with proving these without using epsilons and deltas. That's how I'm sort of biased toward these kind of things. So I'm saying, oh, multiply whatever. Should be okay. Of product rule. Okay. What do I need to do? I need to approximate this up to first order. Okay. Expand. Okay. This is the expansion of this expression times the same thing for g. Multiply everything. These two gives me the first order term, fg at x star. This by this plus this by this gives me the first order term. Times h, and then this by this, that's little o, this by this, it's something that decays even faster than h, so I can just get rid of it. This by this decays like h squared. This by this, well, we did that. This by this, this by this, this by this. Everything else, you see, is something that decays at least as fast as, or more faster than h does. So I can just absorb everything into one little o like this, and that's my formula. That's the end of the proof. If you try to do the same thing using epsilons and deltas, which I would suggest you do, you're going to see it takes a lot more time. Okay? This stuff is very convenient, little o stuff. Okay, that's it for today. We're going to continue on Friday. Thank you. Okay, let's start. Good morning. So today I want to start talking about mean value theorem type stuff, connected to more sort of Calc 1 looking ideas, critical points, regular points, and so on. If time permits, we're going to start talking about the inverse function theorem also. This is basically a theorem that guarantees that under certain circumstances, a function that is differentiable has a differentiable inverse. In other words, it's a diffeomorphism. We had a similar thing for the context of topology, or for the continuity context. We said, oh, if this, that, the other thing, then if it's a homeomorphism immediately. We want to have a similar thing, but adapted for differential calculus. But you know, if it turns out to be the case that we don't have time, we'll just discuss that inverse function theorem business when we come back. Okay. So first, as usual, standing assumption is I and j are non-empty open intervals. If I have a function f from I to j and some specified point x star in I, well, then I'm going to call x star a regular point of f if f is differentiable at this point and its derivative is not 0. Of course, the picture I have in mind is if this is my interval, if this is like this, in order for x star to be a regular point, well, I should be able to talk about this tangent line, basically. And I want this tangent line to be not horizontal. I want it to have positive slope or negative slope. That's what I think of that's what I imagine when I'm thinking of a regular point. Reg of f, this is not standard notation. There is not quite standard notation in this business. I just write it like this. Reg of f is the set of all regular points. And if a point is not regular, you call it critical. Meaning either derivative doesn't exist at this critical point, or if it exists, it is 0. So this would be a regular point. But if I had, well, maybe I'll draw a better picture perhaps. So here's a nice visual example. Okay. Say, start here. Say there's a discontinuity. Then there's a kink like this. And then this is what happens. Okay, so this is my function, say. Here is where we have a discontinuity, meaning at this point, because the function is discontinuous, it is also not differentiable. So that's a critical point. Here, there's a kink. As you see, the left derivative doesn't match with the right derivative. That's also a critical point. Even though the function is continuous there, there's no derivative there. And another thing perhaps is, well, if you look at this, here the derivative exists, but it is 0. Or here too. These are also critical points. Okay? So you should expect, so the general heuristic should be that most x's in I are regular. That's why you call them regular. And critical points are where bad things happen. Okay? So you see, in differential calculus, we don't think about functions like, oh, you know, f is like 1 if x is rational, 0 otherwise. We talked about this function in the context of integral calculus, but for differential calculus, you should not be looking at functions like this initially. Differential calculus is a lot more intuitive. Presumably, I would speculate that if if Newton was alive today, or if you resurrected Newton and told him to talk about this function, he would be like, "What are you doing?" It's like, "What is this?" You're sort of, "What are you trying to do here?" He would just not. Yeah, he would not really consider this as a well-defined object, probably. So, okay, so that's that. If you look at the images, well, a regular value is some height coming from some regular point, and a critical value is some height coming from some critical point. Meaning, these are the critical points or regular points, and then if you look at the heights, so for instance here, that's a critical height or critical value. That's a critical value. There's one here, there's one there, and so on. Again, most values in the image of f you should expect to be regular, and critical things is where things change. Okay. So I'll define one more thing: local maximum and minimum. This is fairly general, so I'm going to state it in the context of metric spaces. Let X be a metric space. And f be a function on X taking real values. A local minimum is the minimum of some restriction of f to some small ball. So minimum of f is how to say, let me see how I stated this. Oh, I'll say it this way. I'll take an x star as well. X star is a local minimum of f, is a better way to say this. Of f if for some delta, if there is a delta positive such that f of x star is the minimum of f restricted to this open interval of diameter 2 delta centered at x star. Oh, I should probably say the open ball in this case then. Sorry. So in our notation, this should be x star less than delta. This is the set of all points that are at most, or this is a set of all points in x that are not more than delta away from x star. So you look at this restriction, and you want this to be the minimum of this restricted function. And likewise, you call x star to be a local maximum if instead of a min you have a max. Local maximum of f if for some delta f of x star is the max of f restricted to the ball centered at x star of radius delta. Like this. And what's the picture here? Of course, it's something like this. If you have a function like so, so for instance, this height would be a local minimum. Why? Because while at large it is not the minimum of f, you see there's a lesser point here. If you were to just focus your attention to some small interval centered at this, okay, and if you just look at this little piece, this restriction, so this is x star, this is plus delta, this is minus delta, and this little piece is the graph of f restricted to x star minus delta, x star plus delta, open. For this restriction, you see this is the minimum. It is not the minimum at large, but locally it is. Okay. And likewise, for instance, This right here is a local max. This is a local min, and so on. And if it's either one of these, you call x star a local extremum. Local extremum of f if it is either. It is either. Now I want to say this, or maybe I should give an exercise. We talked about how a continuous function defined on a closed and bounded interval attains its max, in which case it's the global max, of course. But if I were to take a continuous function defined on an unbounded interval, it may not necessarily have a global maximum, but it always has a local maximum. It's a very nice exercise. Let's say f be a C0 function, continuous function defined on the whole reals. So C0 are R. Then while f may not have a maximum, in other words, global maximum, it's always going to have local maxima. Then has local extrema. Okay. Okay. So what I want to do is this. I want to somehow connect the idea of a critical, or rather local extrema, to critical points. Namely, if I have a function, let me think. I believe, do I need to assume that it is continuous? Let's see. I guess I do. If I have a continuous function on the open interval I, and if x star is a local extremum of it, then x star is also a critical point for the same function. So let's say theorem. Let f be a continuous function from I to j. Maybe I should have changed this exercise to this, in fact. And x star be a point in I. If x star is a local extremum of f, then it has to be a critical point of f. I should say it like this, of course, if f attains a local extremum there. No, it was correct. All right. Is a local extremum of f, then x star is a critical point. Apologies, I'm kind of discombobulated today. Our landlord is doing some renovations, or decided to do some renovations at the house, and everything is very chaotic. Okay. And as usual, I just left my wife to handle all that stuff. So my mind is somewhere else. Okay. So in the textbook, when you look at this, they prove it, Taylor proves it for global extrema, But in fact, the argument really works for local extrema. And I believe in the textbook, there's a direct proof. I find it much easier to go backwards. In other words, assuming that x is a regular point, I find it a lot more easier to show that x star cannot be an extremum. So I'll do that. Say x star is not a critical point. In other words, say x is a regular point of f. In other words, this means that f prime at x star exists and is not 0. That's what it means for x star to be regular. It's a nice input value. Thus, f prime of x star, this number, exists and is non-zero. Without loss of generality, we can just assume that f prime of x star is positive. Okay. I want to show that x star cannot be a local extremum. In other words, it's neither a local minimum nor is it a local maximum. Okay? It has to fail both. And in order for that to happen, I should be able to come up with 2 points sufficiently arbitrarily close to x star such that certain things happen. So here's a picture as to where we are. Just draw it here. So we're in this case. Okay, so here's x star. Here is f of x star. And I'm assuming that x star is not, x star is a regular point and f prime there is positive. So the graph approximately looks like this. Okay. Well, I'm going to try to open up the definition of f prime at x star existing to essentially argue that in this case, well, there's going to be a point arbitrarily close to x star where the image is strictly less. Hence, that would allow me to conclude that x star cannot be a local minimum. And likewise, I'm going to do the same thing from the other side, which is going to give me some point whose image dominates the image of f of x star, concluding that this is neither a local min nor a local max. That's the idea. Right, if you want, you can negate this statement that would say for any delta, right, so f of x star, I want to be not equal to the min. In order for that to happen, there has to be some point delta close to x star such that f of that point is strictly less than this. Okay. So opening this up, we have this. Zeroth order term, first order term, and then higher order terms. We have that this is positive. That's our assumption. Okay. This works for any h. It could be positive or negative. But the point is this. For h small, the effect of whatever this error is going to be significantly less than the effect of this. This is a higher order term. Imagine this is something like h squared. It's something that decays faster than h does. Say this is h squared. For large h, the effect of this matters, but for small h, doesn't matter. Okay. Then what I can say is this. Because this number is positive, if h is positive, this is going to be positive. Okay. And therefore, this whole thing is going to be greater than this. So for h sufficiently small, I'll write it like this. Well, it's okay. If h is positive, this too is going to be positive. And no matter what this guy is, the effects of this is always going to dominate this, which means that this is going to be strictly greater than f of x star. Okay? This concludes that x star is not or cannot be a local max. And similarly, if I were to take h negative, but again sufficiently small in absolute value, similarly, for h negative with, no, I can write it like this actually. For h sufficiently small, in this expression I can replace h by minus h to get this. F of x star minus h equals f of x star minus, because I'm replacing h with minus h, this guy times h. Little o doesn't change. But this time, since this is positive, this is going to be strictly less than f of x star, concluding that x star cannot be a local min either. That's how you finish it. So you see this little o business is very similar, very close to the types of pictures you would actually draw. It's a formalism, but they are a lot closer to pictures, I would think. Okay. And so local min or max implies critical, or contrapositively, regular implies it cannot be a local min or local max. But you see, now we want to sort of upgrade this to some sort of a mean value theorem. In the world of continuity, for metric spaces, I told you the main inequality is the triangular inequality. In the context of differential calculus, the main inequality is the mean value theorem. We're going to state mean value theorem as an equality, not inequality, but you're going to, I mean, those of you who are going to take the advanced, the sequel class, you're going to see mean value theorem in multivariable actually is an inequality. In one dimension, somehow we're able to state more than we're allowed in general settings. So I'll write the statements, all of these statements together. So, Rolle lemma okay. In fact, I'll delete this. This basically says this. Okay, if I have a differentiable function, then between any two zeros of this function, there has to be a critical point. In other words, if I have a function differentiable whose graph passes through this point and through this point, okay, there has to be some point in between where the derivative is 0. In other words, if this guy is going up, it has to come down, which means that there has to be an apex like this. There could be multiple, could be oscillating like so, but there's at least one. Okay, so let's write it like this. Let f be differentiable from I to j, differentiable then for any two alpha and beta for which f is 0, so in the same level set at height 0, then for any alpha and beta in the preimage of 0, if alpha is to the left of beta, then the open interval from alpha to beta has at least one critical point. I'm saying f of alpha is 0, f of beta is 0. If that is the case, and if I have differentiability, then that implies that there is some point strictly between alpha and beta where f prime is 0. Okay. That's the first statement. I should mention this too. Critical points of a function is the points where the derivative doesn't exist, or if it does exist, derivative is 0. But if we're starting with a differentiable function, this is nothing but the 0 set of the derivative function of f. That's the first statement. So this is Rolle. With mean value theorem, it looks like it's a generalization of Rolle lemma, but I would argue it's the other way around. With mean value theorem, you do something like this. Again, you take a differentiable function, like so. Okay, maybe it's at different heights. You look at the line segments connecting these endpoints. So you draw this triangle. Okay, that gives you a line. Mean value theorem says there's at least one point in between these 2 points where the derivative of the function is exactly the slope of this line. In this case, for instance, like so. There's multiple. It's almost like if both of these points were at height 0, that gives you Rolle lemma. If you allow arbitrary heights, that gives you mean value theorem. So you can write it like so. Mean value theorem. Maybe I should say this is the mean value theorem for differential calculus, because I think in the problem set due this Friday, there's a mean value theorem for integral calculus. With integration, you do it. This is for differential calculus. Okay, let f be differentiable. Differentiable. Then for any 2 points, alpha and beta in I, say alpha is to the left of beta, there is an x star strictly between alpha and beta such that the rise over run coming from this triangle is a derivative at that point. Such that, what do I want to say? I want to say f prime of x star is rise over run. Okay. Finally, we have a variant of this. Just like in the problem set that you're working on, there's sort of variants of this mean value theorem for integrals. There's a variant that corresponds to that variant in the context of differential calculus. This is typically attributed to the mathematician Cauchy again. People would often call this the Cauchy mean value theorem, or Cauchy's mean value theorem. It's a generalization of the standard mean value theorem, where in the denominator, you're imagining beta, for instance, to be identity function at beta, alpha to be the identity function of alpha, and instead of the identity function, diagonal function, you replace it by some other differentiable function. So you take two differentiable functions from I to j, be differentiable, then for any alpha and beta in I, with alpha to the left of beta, there is one x star strictly in between such that a similar thing holds. Such that I'm going to send this to the other side, so I want to write it like so. F prime of x star times g of beta minus g of alpha equals g prime of x star times f of beta minus f of alpha. Okay. Yeah.
Does it have to be identity function?
What do you mean?
You say that from the mean value theorem, the beta and alpha, beta is the identity function.
No, I meant this. It's like if you have this formula, if I were to choose g of x to be x, I would get the mean value theorem.
If you were to choose what?
G of x, the g function, to be x,
Oh, that's identity function.
yeah. Yes. It's the function that doesn't do anything. Yeah. Okay. Let's see. This is slightly harder to visualize. One way to think of it is by thinking sort of g to be sort of transforming the horizontal axis as well. There's also like a two-dimensional, so like you can sort of interpret this equation as a statement about sort of curves in the plane under certain circumstances. But yeah, so these are essentially all the same theorem. Okay, I quite like the Rolle lemma. I think it is the most useful. But before I look into this, I'm kind of stuck with this theorem again, and I'm trying to see where exactly I'm using this continuity. Oh, yeah. It has to be continuous because otherwise this is not necessarily close. No? Let's take a break here, perhaps. Try to think about where exactly I'm using this continuity assumption in this previous theorem. If x star is a regular point, then f prime of x star exists. And f prime is, I can assume it to be positive. That's by definition of a point, of a regular point. I'm not quite seeing where we're using this continuity assumption, to be honest, right now. I'll think about this and I'll update you later. We're going to use it for continuous functions anyway, but because ultimately I want to prove Rolle lemma, and we had shown how differentiability implies continuity. So the way this is stated certainly works for our purposes. But for its own sake, it's good to think about where axioms are being used or hypotheses are being used. Anyway, let's first try to do a Rolle lemma. I had said this, but let me write it explicitly as well. For differentiable functions, critical points, or the set of critical points, is the same thing as the set of zeros of f prime. Here, Mike. For f differentiable, its set of critical points is the same thing as the zero set of its derivative. Proof of Rolle. Okay. Now, in principle, of course, f may not have any zeros. But Rolle lemma works assuming that you have two zeros for f. I have a differentiable function, and I'm given 2 points, alpha and beta, such that f of alpha and f of beta are 0. We're given that f is differentiable and f of alpha is the same thing as f of beta, and it's the same thing as 0 also. And I want to find some point in between. Where you have a critical point. What I want to do is, I want to use this theorem that I erased, which tells me any local extremum is a critical point. So what I can do is this. Because I know that beta is strictly greater than alpha, there is an epsilon such that alpha plus epsilon, beta minus epsilon, this closed interval, is a subset, proper subset, of the open interval. Okay, why do I want to do this? Because ultimately, since I know that f is continuous, I know that I can apply the maximum principle to it insofar as I'm looking at it on a closed and bounded interval. So in principle, I can't apply the maximum principle on f on this alpha beta open interval, but I can sort of restrict it, shrink it just a little bit to get a compact interval like this, alpha, beta, and I want to get this. This is alpha plus epsilon, this is beta minus epsilon. I'm going to apply the maximum principle to f here. By maximum principle, applied to f restricted to this smaller interval, we have that there's at least one x star in this smaller subinterval where f attains its max. There is some x star in this closed and bounded interval. Such that this is the max of this function, meaning x star is a local max of f. That is a local max of f. But since epsilon is positive, this x star cannot be equal to alpha or beta, which means we have that x star is in this open interval. It's neither alpha nor beta. And furthermore, by the previous theorem, since local extrema implies critical points, x star has to be a critical point also. And by the previous theorem, x star is also a critical point. And that's the end of the proof. Apologies. It's a nice change of pace, before the break. Usually the classes end up being rather intense. We're sort of taking our time today. Okay, it's like this. This is how you prove Rolle. You see, it's a consequence of the maximum principle together with this idea that local extrema implies critical. Okay. So that's Rolle lemma. For mean value theorem and Cauchy's mean value theorem, the name of the game is to engineer a function to which we can apply Rolle to get the point we want. Okay? And so I want to rephrase, for instance, this equation as, oh, x star is the critical point of some function. And likewise, I want to say this is equivalent to saying that x star is a critical point of some other function. So we need to figure that out. Okay? So for instance, what I can say here is this. If I want this equation to hold, and I want this to be equivalent to saying that x star is the critical point of some other function, well, that means that somehow I need that function to be so that when I differentiate it, it kind of gives me a formula like this. And so here's a nice way to search this. I'm going to start with f. That's a function to begin with. And I'm going to add a small affine function, is what it's called. So proof of mean value theorem for A0, A1, for two real numbers, I can consider this function. Phi sub A from I into reals, that takes an x and sends it to f of x plus A0x plus A1. Or maybe I should have said it the other way around. A0 plus A1x. So I started with f, and I'm adding to it an arbitrary degree 1 polynomial. Okay. I'm going to try to come up with specific values for A0 and A1 such that things work. Let's first note this. Phi is differentiable because it's the sum of two differentiable functions. It's differentiable. It's differentiable. What else? At alpha, what is the value it takes? F of alpha, I'm assuming is 0. Alpha 0 plus alpha A0 plus A1 alpha. At alpha, it takes this value. At beta, again, if I plug in x equals beta, this is going to vanish by the hypothesis. Oh, hang on a minute. That's not my hypothesis. I'm not assuming that f vanishes there, so I just need to add it. F of alpha plus A0 plus A1 alpha. And phi sub A of beta is f of beta plus A0 plus A1 beta. I have these rules by just plugging it in. And then furthermore, its derivative, I have a very nice expression as well. Phi prime sub A at an arbitrary point is f prime plus A1. I just did calculations. Now, what do I want to do is this. I want to choose specific values, A0 and A1, so that if I apply Rolle lemma to phi sub A, I'm done. Okay? So that means, probably I'm not going to be able to finish writing this up. But, oh, and furthermore, I want the critical points of phi sub A to be the same thing as solutions to this equation. In order for that to happen, well, this has to be minus this. Okay? And in order for me to be able to apply the Rolle lemma, alpha 0 should be chosen so that both of these are 0. Okay? That's what we're going to do. Unfortunately, I'm out of time. So we're going to continue doing this after the break. Have a nice break, and I'll see you in, I guess, 2 weeks. Thank you.